Morning, everybody. The warning on the screen is not meant to scare you, okay? But I do have to warn you about something. You are going to walk out of the door today being a different person than the one that walked in. Because I need to tell you something, right? That is going to change how you think about the world and the universe that you live in. Okay, so I think the opening lines of this lecture really need to be open your minds. Guarantee there's going to be a point today, this morning, when you're going to be sitting there going, this isn't true. This is just physics mumbo jumbo. This is just like, physicists trying to sound self-important, or it can't possibly be this way. Your mind is going to recoil from what we are going to learn today. And the most important thing that you can do is to open your mind to the possibility that what I'm about to tell you is true. Because up to this day, more or less everything I've taught you, lie might be too strong of a word, but I've certainly been hiding things from you. And I've told you over and over again that I hide and lie and try to make things easier. But as we start our modern physics unit, what we are going to do is to start telling you about how things really are. And so it's exciting, but it's also can be a little bit unnerving, okay? And there'll be some existential questions and things like of that nature, right? But please, please, please try your very best to open your mind to the possibility that what we're about to talk about does in fact happen. It's going to be 4 days, 4 class days, before I can show you the evidence, the actual experimental evidence of everything we're going to talk about, okay? So hold on for that because the evidence is coming. All right, we need to go back to this. And let's make sure it gets on your screen so you can see it. All right. We left off, before we did all of this optics stuff, we had gone through Newton and Young and Maxwell, black and white photography, flipping back and forth, right? Between the nature of light. Is it a particle? Is it a wave? And we haven't asked, okay, this guy. And this is a big name, right? Like Albert Einstein is synonymous with, genius and science and physics. It's a well-earned place to be, right? I personally think greater than Newton, but I don't have a very big opinion of Newton myself, okay? This is an actual picture. This isn't AI generated or anything like that. The photographer said, "Hey, Doc, give me a face." And that's what Einstein came up with, right? Okay. He was a pretty playful individual, very deep thinker. Oh, well, but you can't really tell. Yeah, it's a black and white photograph. And yes, the flash, he was probably in a dark room and the flash went off and now he's blind for life. But Albert Einstein grew up in a world, right, that was very slowly making its way towards war. Late 1800s, early 1900s, writings on the wall for World War I. And then after that, the racism against the Jews, the awful brutality of the Third Reich. All of these things are backdrops, right, to Einstein's life, he himself being Jewish. And in all of it, I'm going to use the word childlike. And I don't mean childish, right? Because there's childish things, like poop jokes are childish, right? But childlike wonder, that pure innocence and joy at discovery. These were very core to Einstein's sort of being. And it really drove a lot of how he thought about the universe, how he thought about physics. He went to school to be a physics teacher. That was his goal. And after, I think it was 7 applications to various schools to be a teacher, being denied at all 7, right? He finally just took a job that a friend's father kind of mercifully gave him as a patent clerk. Probably the best thing to ever happen to Einstein. One of those stories, right, where people feel like they're just not getting what they want or what they deserve and all that kind of stuff, and then it turns out that the thing that they got was the best thing ever for them. Because being a patent clerk 3rd class in Bern, Switzerland, meant that Einstein had time on his hands. Like, the actual clerking part didn't take up very much of his mental process. It was like stamping pages and just making sure the patents were filled out correctly. What it did is it exposed him to the technologies of the day, particularly time and timekeeping. And he was always fascinated with time. It also gave him, he had extra computational cycles, not because he was a genius, but just because of his work wasn't very mentally demanding. He had this extra time on his hands to really dig in and start thinking about the universe. And the nature of light was something that really drove Albert Einstein. Okay, he really just he had to know what it was. And he worked hard at trying to conceive of it. And in the end, it ended up reinventing our understanding of how the universe works. So let's see if we can't kind of dig in, okay? And again, I'm going to come back to what is light, right? Because we have to discuss Einstein's sort of take on it. And we'll come back to that. Again, we're sort of putting a pin in it, and we're leaving this theme of what is light as a constant undertone. What we're going to do, though, is we are going to do a little bit of a tangent right now, because there really isn't a better place for this subject to fit in our curriculum than now. We've mentioned Einstein, and what does everybody know Einstein for? E equals mc squared, right? So E equals mc squared is not going to help us understand what light is. We're going to circle back to that and get back to it. But we do have to talk about E equals mc squared, where that comes from, context, why we understand the universe to be different than we did before Einstein, all that sort of stuff. So that'll be our tangent for the next couple of weeks, right, is trying to come to grips with what's going on there. Einstein, in 1905, I believe that was the year, wrote 4 papers, or at least submitted 4 papers. These were papers that he had been working on while he was working as a patent clerk and other things. And it's often called Einstein's miracle year, this year of these papers. And this is a copy of an original, or maybe a picture of the original. Of course in German, because he was a German national, born and raised. And what's remarkable about these 4 papers, okay? 2 of them have to do with relativity, which we're going to get into today. And then the other 2, one was on Brownian motion. I'm not going to mention it ever again except in passing. But what the paper on Brownian motion is the random motion of objects in a medium. So have you ever tripped out kind of on the dust mote floating in the sunshine? And you just kind of, because the rest of life is too hard to think about, you're just going to think about that dust mote, right, floating through the air and what's it doing. That motion that the dust takes is called Brownian motion. The motion of molecules in a mixture is Brownian motion. And so Einstein's paper on Brownian motion, like, was the final word that atoms and molecules exist. Like, they had been like experimentally sort of pointing in the right directions, but until Einstein wrote his paper on Brownian motion, there was some uncertainty. Maybe there was a different mechanism. But after this paper, no, atoms exist. We don't have to keep debating this. So that was like pretty impressive all by itself, and I will never mention it again because it was the least of the important papers of that miracle year. One of the papers was on something called the photoelectric effect, which we are going to get back to because it has everything to do with Einstein's opinion of what light is, right? And then the final two, I'm not giving these in the order of publication, were on the special theory of relativity. The first paper was like the conceptual framework, and then 9 months later, a second paper came through that had all of the mathematical framework behind it. Einstein wasn't great at math and needed a lot of help with the math, and he got lots of help from friends and colleagues. So 4 papers in this miracle year, right? They come out, and except maybe for Brownian motion, nobody really pays attention. And they are quite remarkable. The 2 papers on relativity are quite remarkable for what's missing. Usually, even in this, back in the day, there would be lots of references to prior work. So-and-so had done this experiment. So-and-so had done this theory, right? And then you sort of take off from the work that others had done before, and you're taking it in a new direction, or you're refuting a theory, or you're doing something, right? But you're always basing it on something that came before. Special relativity paper hits, and there's no references. Like, not because Einstein was lazy or couldn't write a reference paper, but because there was nothing to reference. This is brand new ideas. And it came out of a desire. This was core to Einstein, okay? This concept and idea that there is one framework in which to explain how the universe works. The problem that Einstein had with physics is that you had Isaac Newton and all of Newton's laws, right? Explaining orbits and how to get places and all that kind of stuff, right? And you had Maxwell's equations, which of course was the work of Faraday and others, but like we can summarize that there was this other way of describing how the universe works. There was the universe of Newton, of particles and objects and torques and orbits and, right, give me the initial conditions of the universe and I can tell you what it's going to be like 100 million. It's very deterministic. And then you had Maxwell's equations and electricity and magnetism, which was field theory, which was all about electric and magnetic fields and what they do and how they interact, and of course light and how it interacted with stuff, and optics and all those kinds of things. And there is almost an inherent conflict in those 2 ways of conceiving about the universe. It's a little bit like having 2 different sets of traffic laws depending on like which way you're going. So let's imagine that going north on Blackstone, it's the normal, red means stop, green means go, red means stop, and yellow means burn rubber, I guess, because that's what people do, right? But going south on Blackstone, yellow means stop, red means go, and green means burn rubber, right? Like, do you see how you would lead to confusion and accidents and all kinds of problems to have 2 different sets of traffic laws that depended on which way you were going? This is what Newton versus Maxwell is like for Albert Einstein, right? There's these discrepancies and these conflicts and different ways of looking at the same things. And to Einstein, that meant that one or both weren't wrong, but weren't complete, okay? And so he set out to complete them. That was his goal. What framework do we need to work in so that Maxwell and Newton can agree and we can explain everything that's going on in the universe? So he sets out two rules. These are like the two conditions upon which his theory of relativity, and notice I'm using the word theory, not hypothesis, not guess, because this has been confirmed. And again, evidence comes later, okay? But he lays out two statements that form the bedrock of all the assertions and all the experiments and everything that's going to follow that we're going to learn today. The first of these postulates is a basic statement that it says what it is what it says on the tin. That is to say, the laws of physics work everywhere, right? It kind of really doesn't matter who's doing the looking or where you are, okay? We can do an experiment here in Fresno, and somebody in LA can do the same experiment. We're going to get the same results. So we could be here in Fresno, somebody could be on the moon, right? And they do the experiment and get the same results. Of course, knowing that gravity is weaker on the moon, and we can correct for that. Like, what Albert Einstein is trying to say, that the laws of physics are the same everywhere. He does put a condition, though, on this: the laws of physics are the same everywhere. And he uses physics terms for it, okay? Inertial frame of reference. A frame of reference is like a coordinate system. It's like a way of measuring things around you. We often default to X, Y, Z, right? Where we are in space. Inertial is coded physics language for no acceleration. So if you're in an accelerating frame of reference, think of the International Space Station. The International Space Station is going around the Earth. It's in free fall because gravity is the only thing acting on it. It's just not getting any closer to the surface of the planet. That's what an orbit is. When you're on the International Space Station, it looks like the laws of physics are different. It looks like there's no gravity when in fact there is, right? You throw a ball, you play catch on the International Space Station, you don't need to arc it, right? You can just push it straight because it's not going to fall, in quotes. So the International Space Station is not an inertial frame of reference. It is an accelerated frame of reference. And so it appears that the laws of physics are different. The reason this theory is called the special theory of relativity is because of this assertion that we can do no acceleration. The general theory of relativity, which we'll get to in about 3 days, is the one that incorporates acceleration. So he starts, because it's much easier to start with no acceleration, and builds from there. So that's the first postulate. The second postulate is the one that changes everything. And I know sitting there reading it, it doesn't seem like it should. It's kind of a, well, duh. What is the speed of light? The same. For who? Everyone. Regardless of what? Of how fast they're going. On the surface, you're like, yeah, speed of light's the speed of light. What's the big deal, Mr. Balogh? This is foundational and earth-shattering to our understanding of how things work. And so I'm going to take a page out of Einstein's book. I'm not going to do exactly his thought experiment that he came up with, but we are going to do, this is something, again, that Einstein sort of pioneered, right? This concept and idea of, let's do an experiment that's impossible to pull off with the technology that he had at the time. So he called it a thought experiment, but it obeyed all the rules of his postulates as stated, which in the end, again, sounds like philosophy, right? Sounds like a logic problem, sounds like a philosophical. It's not science until there are testable outcomes, right? And then we can do experiments to verify. I'll explain the experiments later, okay? let's talk about the implications of these two postulates by doing a thought experiment. I need 3 volunteers. You do not have to get out of your chairs. Truman, Sim, and who else? Karen? Okay. Let's see. Truman.
Yes.
You have a car?
A car?
Yeah.
No.
No? Sim, do you have a car? Okay. So, do you like your car, Sim?
Yes.
Okay. So let's see here. We're going to have a situation, okay, where Sim is in her car. How'd I do? Yeah. No, it's not great at all, but you get an A. Okay. Sim is driving along, let's say at, I don't know, let's do 50 miles an hour. Okay? And Karen is standing by the side of the road and is holding a like a radar gun. Okay? And is using this radar gun to measure the speed that Sim is driving by, right? So the 50 miles an hour, as stated, is measured by Karen on her radar gun, and by Sim looking down at her speedometer, right? It reads, we'll assume everything's calibrated correctly, right? But 50 miles an hour, right? Okay, all right. I know that Truman is much smarter than this. He would never, ever do this. But for the sake of the purpose of this experiment, let's just say that Truman is on the hood of the car. Okay? And Truman has a baseball in his hand. Okay? Truman, you throw a good fastball?
Yeah.
What? 50, 60, 80 miles an hour? What do you think?
Probably
It's a thought experiment. Go for the gold, man.
60's average.
60's average?
Yeah.
So 110?
You sure?
Okay, all right. Truman throws, jeez, at 110, throws a 110 mile an hour fastball. By the way, I think the fastest clock fastball is like 102, 103,
Yeah.
106.
You'd have to be pretty
Okay, right? So yeah, Truman is like world class here, right? Okay. So Truman throws the baseball at 110 miles an hour, according to Truman, right? This is Truman's pitching speed, right? 110 miles an hour is also what Sim, like if Sim had a radar detector and she's looking at the ball, right? Okay. It would be the speed that she sees the ball going at, right? But what does Karen measure the ball going at?
before addition.
So 160 miles an hour?
That's what I'm thinking, yeah.
Yeah, that's exactly what Karen would measure. Yeah. This is Galilean relativity. Okay? Galileo first set out these ideas, right? That if you have an object moving and another object that moves relative to the first object, then a third observer will see the sum of their velocities. Now, if Truman threw it backwards, right, we'd subtract these two numbers. But this is the essence of classical, we call it Galilean relativity. Okay? Do Truman and Sim together, they measure one thing, and Karen measures something else. Is there a discrepancy in the measurement?
No.
Yes. Yes, there is. Your data, your radar guns,
Right, with the radar gun.
not pictured. There's Truman's radar gun. Okay? Truman's radar gun reads 110 miles an hour. What does Karen's radar gun read? 160. There is a difference in measurement, right? So how do we explain the discrepancy?
I'm thinking that, because I'm also moving, which means baseball
Okay.
is also moving.
So the frame of reference that Sim and Truman are sitting in is in motion.
Yeah.
Okay? The relative speed between the frame of reference of Karen and the frame of reference of Sim and Truman is 50 miles an hour.
Yeah.
Right? Everybody knows this, right? Everybody's aware in this setup, everybody's aware of the difference in relative speed, right? And so they acknowledge that though the actual measurements are different, the difference can be explained by the relative velocity between the frames of reference. Is everybody okay?
Yeah.
This is the part that should make sense. Because now I'm about to break your brain. Because now we're going to apply the second postulate of relativity. Okay? So, second postulate. Let's, Sim, do you like to drive fast? Yeah, sometimes. Okay. I don't advise it, but okay, for the sake of this problem. Let's say that Sim just pedal to the floor. Like pedal through the floor. Like just nails it and speeds up to 99% the speed of light.
Whoa.
It's a thought experiment, right? Okay, we can do whatever we want. Okay, except break the first postulate, which is break the laws of physics, right? Okay. Truman swaps out his baseball for a flashlight. Okay, and turns on his flashlight, big flashlight. Okay. What speed does the beam of light coming from the flashlight travel at? The speed of light.
Yeah.
Okay, because it's light, right? So it moves at the speed of light, 1 times the speed of light. By the way, in relativity, we often say like percentages of the speed of light, right? 0.99 c is 99% the speed of light. All right. What does Karen measure? What does she measure the beam of flashlight speed to be?
I don't know.
The second postulate tells us. She must measure the speed of light as well. Not okay.
No, it's not.
So far from not okay that we are going to have to rewrite everything we understand about the universe, what it's made of, and how it works. I can tell by your faces that you either don't believe me. I told you there's going to be a point where you're just going to be like, this is stupid, right? Push past that feeling of this is ridiculous because you have devices in your pocket that rely on everything I'm telling you right now to function correctly. More on that in 4 days. How could Karen possibly measure the speed of light? Einstein's second postulate says that she has to. Everybody, no matter what their frame of reference is, no matter what the relative speed between their frames of reference is, has to measure what? The speed of light. They must. It's in the second postulate, right? What should it be? Like under Galilean relativity, what should Karen be measuring? 1.99, right?
Yeah.
Just like the baseball, right? Just like Galilean relativity, you just add, right? The car's always going this fast, right? But that's not what Karen measures. Karen measures the speed of light. Sim and Truman measure the speed of light. I often get asked, Mr. Baylor, what does it look like if I'm going near the speed of light and I turn on a flashlight? Like everybody thinks incorrectly that the beam of light would be like moving very slowly forward, right? You could see the individual. That's not what it looks like. To all observers, regardless of how fast you are going, how fast does light go? The speed of light, right? Doesn't matter.
Is the speed of light independent of frames of reference?
Yes. That's what the second postulate says. how can this possibly be true? How can everybody see the speed of light when there is an obvious difference between the frames of reference? This is physics. So what do? You do an experiment. Thank you. Okay? So, let's do an experiment. We are going to invent a device. This is not, again, a real device that we could possibly build and use, okay? But it is a device that uses the most basic principles of physics, in other words, the first postulate of special relativity, to work. And it's called a light clock. A light clock consists of two mirrors between which a beam of light is bouncing. Like it gets emitted, right, from some light bulb or emitter or laser, I don't care what it is, right? Light comes out, right, goes up, bounces off the top mirror, and comes back down to the bottom mirror. And we kind of say the clock is tick-tocking, right, based on the bounces that are happening on the mirrors, okay? And so what we're going to do, so what are the advantages of this light clock? Number one, it's very simple in its operation, okay? Number two, the tick-tock depends on the one thing that everybody sees the same, right? The mechanism of the clock is based on the speed of light, and according to Einstein's second postulate, the speed of light's the same for everybody, and the laws of physics have to be the same in all inertial frames of reference, so we should all be in agreement as to what we're going to measure. So we give one of these light clocks to Karen, okay? So she's holding a light clock, and she's using her light clock, right, to observe and measure what's happening around her. Truman and Sim driving past it near the speed of light. Okay? We also give Truman a light clock. Sim's busy driving. We'll let her keep her hands on the wheel. Okay? And we give Truman a light clock, so he's holding a light clock, right? Okay? Let's talk about tick-tock. The amount of time it takes for the light beam to go tick-tock. If the distance between the two mirrors, okay, is d, I don't know what it is. Let's just call it little d, okay? Then how do we, okay, how would we measure the time? So basic physics, right? Distance equals velocity times time. And so the time will be the distance divided by the speed. What's the distance that the light traveled to go tick-tock? 2d. Right? And how fast was it going? Speed of light. Okay? So who measures this? Karen or Truman? Karen measures it. What's Karen doing? Just sitting there, right? Not moving. Okay. What's Truman doing? No, he's not.
Oh, he's not moving either.
Relative to the clock in his hand, the clock is not moving relative to Truman. So does Truman measure a tick-tock equal to that? Same thing, right? Assuming the light clocks are identical. Okay? Now let's ask the question. Oh, and by the way, that was your first bit of relativity right there. I moved your brain from one frame of reference to another. You live in a society, in a world that tells you that the ground isn't moving. It's a lie. It's a good lie, but it's a lie. Okay? relativity demands that you be able to put yourself in different frames of reference. There is a frame of reference where Karen is sitting still watching Sim and Truman go by. But there is another equally valid frame of reference where Sim and Truman are standing still and they're watching Karen go by. Okay? It sounds ridiculous to say, but nonetheless, the laws of physics allow for you to assume that on the drive to school today, you went nowhere and the school came to you. Do you hear the snorts and the little giggles and the it's stupid? That it's not. Kinematic equations, Newton's laws, chemistry, all of it doesn't care. You can solve the problem assuming that you are doing the one moving or that you are standing still and the road goes underneath you. It is independent of those frames of reference. We tend to go towards the one that makes sense to our brains because obviously we are the ones moving across the ground.
Yeah.
The same reason we thought.
Or are we standing still and the ground is going underneath us?
The ground is moving.
As far as the laws of classical physics can tell you, there's no difference. Those are equally valid frames of reference. Okay, so there's your first little taste of relativity. Back to this, okay? Karen is now going to observe and use her clock to measure the tick-tock of Truman's clock. What does Karen see? When the light beam starts, let's say Truman is right, they're exactly lined up with each other, okay? As Karen watches, right? Truman comes by with his clock. She starts observing right here, right? She sees the light beam start. What is Truman's clock doing, according to Karen?
Something.
Moving this way. Okay? So the beam will not be going up and down according to Karen. Karen will observe that the light clock started here, but then by the time the light beam gets to the top, the clock will have moved sideways, right? Okay? And so it'll be in a different position than where it started. And so as far as Karen is concerned, the light beam doesn't go straight up and down, it goes in a diagonal line, doesn't it? Okay. This is just basic physics. Okay? Again, the laws of physics are the same. Okay. Right? And then that's the tick. What happens to the talk?
Go straight up?
It's going to come down like that, right? Okay. What's this distance right here?
ID.
It's d, right? Okay. What's this distance right here? Ni. If distance is equal to velocity times time, then this distance is whatever the relative speed is times the time it takes to get there. What's this distance? Oh. You could use the Pythagorean theorem? Okay, but before we do the Pythagorean theorem, what is this distance? Not c, because that's just a velocity. That's not a distance. Distance equals velocity times time. What's the velocity? What is this thing right here? It's a beam of light. How fast is it going? C. Right? right? Okay. And then what's the time? T. I've lied a little bit. These should probably be T's over 2 if we're going to be really careful. Because a tick-tock is a full up and down, right? So as far as because down here we said that the time was 2D over C for the stationary clock, right? Because it had to go up and come back down, right? Well, this one has to go up and come back down. So this portion of the movement is represented by only half the time, right? Now, Sim said Pythagorean theorem, which would be C T over 2 squared equals D squared plus V T over 2 squared. I'm looking for it. I'm not seeing anybody's face go, wait, I've seen this before. Where have you seen this before? It's been a while. Lab 1. Problem number, was it 4? I gave you that equation. I gave you this equation with a capital D in it. And I gave you this equation with a capital D in it. And I told you to solve it. This is how I get you to do my job for me. Question?
Is it mathematics?
What's that?
Mathematics?
No. I mean, you don't have to use the quadratic equation or anything like that. You just have to put these two equations together to see what comes out. Okay. We're going to watch some video because the animations are going to help us understand a little bit about what's going on. But before we get there, to contextualize videos and make them have their full impact, does Karen measure the same time interval on both clocks, hers and Truman's? Whose clock, according to Karen, takes more time to tick? Truman's clock. The light has to travel a longer distance to do its tick-tock. Right? So therefore, 1 second on Karen's clock, 1 tick-tock, right, is shorter than the tick-tock on Truman's clock. Don't see it yet?
Light is going slow.
What did I just tell you without telling you?
Light is going slower.
No, light has to do what? Has to travel exactly the same speed for all observers. This is the one thing that Karen, Sim, and Truman all agree on. They disagree on who's moving, and they disagree on whose clock is giving the correct time. Because Karen sees Truman and Sim's clock running slow. Takes a longer time to tick-tock because it has to go a further distance to do its tick-tock. Truman and Sim say, we see you moving, our clock is going tick-tock, but your clock is taking a longer time to tick-tock. What is no longer a constant in this problem? Time. Time is different for these two frames of reference. In fact, Karen sees Sim and Truman's time running slower. In physics terms, we call this dilated time. It's dilated. Dilated is a word that means like gets bigger, or like the spacing between gets bigger. Time, the tick-tock of seconds, is stretched out. It's dilated for moving things. You woke up this morning. Sure. 100, 1,000, 100 milli%, whatever it is you guys, is hundo P still a thing? Please tell me hundo P is not still a thing. It used to be all of cool kids would say hundo P for 100%. No? Okay, good. I'm glad that was never a thing because it was dumb, right? So you woke up this morning knowing that a second was a second. That the time on your cell phone was the time everywhere because it's set by the internet, which is set by the standards organizations of like 3 countries across the world that all synchronize the time. Everybody, there's no excuse to be late anymore. Everybody used to be, before cell phones, we could say, oh, well, my clock said that the time was something different. And people would go, okay. Now, no mercy. So you woke up knowing that time was time everywhere for everybody. And what did I just tell you? That time depends on who's doing the looking. Depends on motion. Time is no longer a constant. Let's see if we can unravel this. Let's see, we'll play this video first. And let's change to this input. And let's see if we can make it work. And I didn't set the time. There we go. Let's go back to the beginning.
The essence of his reasoning can be seen with the aid of the simplest possible clock. 2 mirrors a fixed distance apart, with a light beam bouncing back and forth between them.
That's Henry, by the way.
Each bounce of the beam is a tick or a tock of the timepiece.
Henrik Lorentz.
Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers. So the light must take a longer time to travel a longer distance. Therefore, Albert believes the moving clock runs slow.
Do you see it? Right? Nothing here. I am not trying to pull the wool over your eyes. This is not magic. This is not a hallucination. You need AI for that. This is the laws of physics in their plainest and simplest forms. We are talking about actual, measurable differences in the observations of things. So how do we calculate what the discrepancy is? Remember how with Galilean we figured out it was the 50 miles an hour that was the difference between the measurements? Here's the attempt at figuring out the difference between the measurements. Maybe. Here we go.
The relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors. By the factor 1 over the square root of 1 minus v squared over c squared. This factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
So that's basically what you did. You solved that same problem on chapter 4. You didn't quite get it to like this form right here. Your form might have been slightly different, but mathematically it was the same thing. So they did the math for us, and the punchline as far as the mathematics of relativity are concerned, I mean, the math is pretty simple. There's no other really way to say that, okay? What we call the time dilation equation, I'll do it in green, okay? The dilated time is equal to a factor, the gamma factor, times something called the proper time. And I believe in the problem I made you do, I used this kind of more modern notation here, right? The delta T naught, okay? So in this box right here, this delta T naught right here is what we call proper time. That's going to be very important. We'll talk about it in a little bit, okay? Then over on this side, we have the dilated time. And then we have gamma. Gamma, as they showed us in the video, was 1 over the square root of 1 minus v squared divided by c squared. Again, that factor appears so often in our calculations in relativity that we just call it gamma, we calculate it off to the side, and then we just carry the factor through all of our equations, right? Physicists don't like writing things over and over that are the same, so we'll just give a different symbol for them, okay? Now let's talk about gamma real quick.
Is it v squared over c squared or not?
That's v squared over c squared. Okay, so our v's, like when we do v's, right? The velocity, like how I gave in the other problem, is like 0.99 c. There's a reason we're writing it like that, okay? So if we had to calculate gamma for this 0.99 c, right? That would be 1 over the square root of 1 minus 0.99 c squared all over c squared. What happens to the c squareds? They cancel out, right? So gamma is often, you'll see a physicist say, well, the gamma factor is 1 over the square root of 1 minus 0.99 squared. What just happened? They knew the c's were going to cancel, so they just didn't even bother to write it, right? Okay. So that's why you'll see a lot of the speeds as percentages of the speed of light, decimal fractions of the speed of light, right? What would half the speed of light be? How would you write down half the speed of light? 0.5 c, right? 75% of the speed of light, 0.75 c. You get the idea? Okay. So let's take a look at what the range of gamma can be. What's the slowest something could be moving relative to something else? 0, right? In other words, not moving, right? So when v is 0, what's gamma? In the denominator, we get, so if v equals 0, gamma equals what? It's 1 minus 0 on the denominator. What's 1 minus 0? 1. What's the square root of 1? 1. And what's 1 divided by 1? 1. Okay. So if v equals 0, gamma is equal to 1. That's the smallest gamma could ever be. Gamma can't be less than 1. Okay? What's the biggest gamma could ever be? I haven't taught you this yet, but kind of everybody knows this fact about the speed of light. Sometimes called the universal speed limit. We'll explain why later. 3 or 4 days from now. Okay? What's the fastest anything could ever move anywhere? Speed of light. Okay? So what happens if we put c in for v? So if v equals c, then what's gamma? What's c squared divided by c squared? 1. What's 1 minus 1? 0. What's square root of 0? 0. What's 1 divided by 0? Infinity. Undefined. Math teachers. Okay. So Gamma can go from a minimum value of 1, where two things aren't moving relative to each other, to infinitely large when something moves at the speed of light. Okay? Notice that the gamma factor sits in front of this thing called the proper time. I haven't really defined that yet, but we're getting there. Okay? So for Karen, who's measuring dilated time, right? She's seeing Truman's clock go sideways. And she's saying Truman's clock is ticking slow. How slow? Well, it depends on the gamma factor. Okay? If gamma equals, let's say, 10, okay, then what would Karen measure? She sees her time, her proper time is 1 second, right? But she would see Truman's clock, the time, the delta t between tick and tock, would be equal to 10 times the normal time. So what is the clock doing? If the tick-tock is 10 times bigger, is it going slower or faster? Slower. This can be kind of hard. A lot of times we don't think about what a second is. Okay, what's a second? See? Right? You got 1 second by definition is, I don't remember the number, but it's like 1 times 10 to the 17 oscillations of a cesium atom in an atomic clock. Okay? That's what a second is. Did that help you understand time? Absolutely not. Right? So the question I'm asking is, what is time? We're just doing all the easy questions in Physics 2B. What is light? What is time? Right? So what is time? Time is a measurement between two things. Two events that mark the passage of time. We often don't think of the initial event. We say it's time equals 0, right? And then whatever transpires to the next event, that's just the time. But the measurement of time is always a difference between two events that mark the beginning and the end of the measurement of time. This is very strange. It's one of the strangest concepts I believe we have in all of physics, that this concept of time is measured by looking at actual physical things that happen in space and time. What's an event? An event can be anything. An event could be the beginning and the ending of this class. Class starts at 8, it ends at 9:15. We measure the time interval between those two events, the start and the end of class, to be 75 minutes. Right? An event could be a heartbeat. The beginning of the heart to the returning to the initial condition, right? One lub-dub. Those could be two events, and then we measure the time it takes for the heart to complete that. It could be returning to the same point in an orbit as we go around the sun. It could be the number of cesium atoms jumping up and down. What is a second? A second is, and it says 1. What were the events? Starting the stopwatch and stopping the stopwatch. Right? Okay? Events. Actual physical things that happen in specific places and times tell us what time intervals happen. Okay. So, if gamma equals 1, what do Karen and Truman say about their clocks? They're equal, right? But a gamma of 1 means that Truman is going how fast compared to Karen's clock? Speed of 0. The car's parked, right? So, and we won't talk about yet what happens when sim goes the speed of light. We'll get there. We'll get there. Okay? Okay. Gamma, by the way, if you plot, I know this one says U. We'll use V. Okay? So gamma as a function, right, is not linear. It actually does most of its changing in the very last bits, right, where we're getting close to the speed of light. Notice down here at half the speed of light, it basically hasn't deviated from 1, right? It's really close to its original value. It's only when you get to 3/4 that you start really seeing a difference, and then like all the change is happening in like 0.98, 0.99, 0.999, right, times the speed of light. So gamma isn't linear, and I want to, in the last 15 minutes, we're going to get into a problem. We're going to do it, and it's going to break you if you're not already broken. If you're not already broken, you probably haven't really internalized what I've been trying to say. And it could take you a few tries, right, to really think about it. But I do want to give you something that you can be certain about, right? Something that you can take comfort in. And I especially don't want you arguing with the nice police officer who pulled you over for speeding. But officer, you were the one doing the speeding, not me. That doesn't work. Don't try that, okay? So, what's the thing that you can hold on to that's going to make living life okay after this knowledge? Normal, everyday experience has a gamma factor really close to 1. A car moving at 60 miles an hour, that's a gamma factor of 1, right? 60 miles an hour is like 1/10 millionth % the speed of light. Okay? It's so insignificant in terms of relativity that you're never going to measure any difference in time. Somebody out there in a car that's coming down Weldon, right, is measuring the same time as we are. Now, the International Space Station, it goes around the Earth about once every 90 minutes. It's about a 6 or 7 minute flight from New York to Paris. Okay? So they're moving pretty quick. And if they spend any amount of time up there, like a 6-month stay on the International Space Station, they actually come back younger than they should otherwise be. Now, they're younger by like 1/100th of a second. But they are younger. That's why astronauts always look so fit. That was a joke. You have to be going really fast in order to be able to observe time doing funny things. But we are a species that has achieved a technology that allows us to use light for various things, and so we have to start taking into account these differences. And again, we'll get there. We'll get there. So, how do you survive problems, okay? The math, I really shouldn't say it this way, but it is stupid easy. Like compared to what we've had to do with like vectors and bad algebra and all that kind of stuff, right? There isn't much to it. Right? That's it. There's your toolbox. But the problem is, how do you apply it? You essentially have what comes down to a 50-50 chance of getting it right if you're just guessing. We want to improve those odds. So let's figure it out. What is delta T naught? It's proper time. What is proper time? Proper time is the time interval measured between events that happen at the same location in space. I'm going to say that over and over again because it's really important. It's hard to wrap your brains around because time and time measurement is not something that you are taught. It's just something you assume that you know, and I'm telling you, you don't know half of it, okay? Let me say it again. Proper time is measured in a frame of reference where the events measuring time happen at the same place. Proper time. Knowing whether or not proper time has happened depends on you knowing what? The position of events. Something that begins and ends the measurement of time. Dilated time, therefore, measures a time interval between events that happen at different places, right? So we have to look at the events that are being used to measure time. Is there any time in this problem? There's lots of time, right? There's 1 year. There's 22 years and 17 years. Like there's a lot of times in this problem, right? But as far as the problem is concerned, the 17 and the 22 don't matter yet. What we have to do is we have to look at who's in the problem, what they're measuring, and then determine what it is we're going to do. So who are the two actors? There's always two actors in all of these problems, two people that are observing something, okay? Different frames of reference. Please note that in every problem, these people are smart, have college degrees, whatever it is you want to think. They're not stupid. They're not misguided. They're not making things up, right? They are intelligent individuals telling you what they have measured, okay? Oftentimes, just to get traction into a problem, the very first thing I will do is just calculate gamma. You're given a relative speed, find the gamma factor. So that's what I'm going to do first, even before I do anything else in this problem. It's 1 over the square root of 1 minus 0.99 squared. Where'd the c's go? Where'd the c's go? Just cancel out, right? So I got 7.08. No units. Gamma's unitless. All right. So there's our gamma factor. It's about 7. Okay. All right. What is the time interval that this problem is measuring? 1 year. Okay. So we have a time interval of 1 year. We don't know if this is dilated or proper. We're just given a time interval of 1 year. We have to apply postulates of relativity, definitions of proper time, all of these things to be able to figure out if the 1 year that's been measured is dilated or proper time. What are the clues? Okay. Who measured the year? No. Read carefully. According to the ship's clocks and calendars, right? The 1 year is being measured on the ship. Okay? What do they want us to find? How much time passed on Earth? What I like to do sometimes is I do like to visualize, draw a picture. Okay, so we have somebody on Earth, your sister. Okay, if you don't have a sister, pretend you have one. All of my rocket ships look like carrots, and all of my astronauts are surfing on them. I don't know any other way to draw it. Okay? All right. So, this is what we have, right? This is the situation we've got going here, right? The ship measured 1 year, right? Earth, right? We don't know. That's what the question's asking us to find, right? I better circle that. That's the thing we're looking for, okay? But the 1 year, dilated or proper, don't guess. Don't ever guess, okay? Let's see if we can't figure it out. What are the events that bracket the 1 year? Good. So our events for measuring time are takeoff and then arrival somewhere in a year, right? Okay, those are our two events that happen. Put yourself in the frame of reference of the rocket ship, right? You're measuring 1 year. That's either calendar pages flipping, it's your stopwatch on your... Does anybody know if the stopwatch goes up to a year? Probably not. It's the ship's computers, right? Whatever, right? Are measuring this interval. But the event that starts the stopwatch is leaving Earth, right? And the event that stops the stopwatch is arriving, right, at the destination a year later. Those are the events. So, is the 1 year proper time or dilated time? Again, who's doing the measuring? The ship is doing the measuring. So, according to the ship, where did the beginning and the end of the trip take place? It's not on Earth. Can't turn around. No acceleration. According to the ship. Well, okay. Let's do it from the point of view of the Earth. Maybe that'll be a little bit easier, okay, for us to deal with. What does the Earth see? What does the ship do? It leaves, right? The ship goes from there to wherever it is a year later, right? Okay? Does Earth measure proper time? No. Where is the ship at the start of the time interval? On Earth. Where is the ship a year later? Somewhere else. Not at the same location. So what is Earth measuring? Why is it dilated? The location of the events that mark the measurement of time are in different places. So Earth is measuring dilated time. So how could... Almost out of time, speaking of. Actually, if we run really fast, we can lengthen this class, right? That will not be an excuse on your exam for more time. Why does the rocket ship measure proper time? Where is the rocket ship when it starts its trip? Wherever it is. Where is the rocket ship when it stops its trip? In the same place. From the point of view of the rocket ship, what did the Earth do? And they stayed still. It's not like it is like that. It's exactly what it's like. So, what does the Earth measure? Delta T is equal to 7 times delta T naught. What's the proper time? So 7 years. The trip that takes 1 year for you, according to your clocks, on Earth, 7 years have elapsed. You were 22. Now you are 23. Your sister was 17 but has aged 7 years. She's 24. This is real. We obviously haven't done this experiment exactly. But we've measured the growths of plants. We've measured the lifetimes of subatomic particles. We have measured time dilation as it happens in the lab and in the universe. And this is what happens. Hold on to that. As you, well, is it time travel? You're all time travelers. You are moving through time. You don't have a choice. Right? It's just simply a question of how fast you're doing it. We'll reconvene on Thursday where I will continue to blow your mind. Only this time, it's going to be distance that pays the price.